Hello everyone, myself Piyush and Tandil, working as Assistant Professor in Electrical Engineering Department of Mahatma Gandhi Institute of Technical Education and Research Center, Navsari. And the name of subject is Industrial Instrumentation, which comes in 4th year, 7th semester. And today we are discussing about the strain gauge and strain measurement, and this is the module number 3. So first of all, starting with flow of content. So in this video lecture, we are going to see the material for strain gauge. Then after, the strain gauge characteristics. So which characteristics strain gauge should have to perform in optimum condition. Then after, wire resistance material. So which kind of material we are going to use for our resistance wire. Followed by the backing material, adhesive, leads and gauging techniques and other factors that are going to affect our measurement. Now, material for strain gauge. The materials that are used for fabrication of strain gauge and their installation for stress measurement must have some characteristics and minimum standard to obtain high accuracy, excellent reproducibility and good sensitivity, long life and ability to operate under required environment conditions. So our instrument or our measuring device should be very much of reliable. It has some good characteristics and minimum standard to obtain high accuracy. So accuracy should be high and excellent reproducibility. The reading should be very good sensitivity, so small amount of change in input output can be sensible. Then after, long life and its ruggedness regarding the environment of the condition. Then after, the strain gauge must have the following characteristics. So strain gauge should have some of the characteristics to perform in good condition, right? So the value of gauge factor G. What is the value of gauge factor? That is must be high. So why we are requiring the value of gauge factor should be high? A high gauge factor indicate a large change in resistance for a particular strain, resulting in high sensitivity. So what is our equation of gauge factor? The equation of gauge factor is delta R by R divided by delta L by L. And what is delta L by L? That is our particular strain. Okay, what is delta L by L? It is our strain. So at low value of strain, the change in resistance should be high. At that time we can call as a large value of or high value of gauge factor, right? So it could have good sensitivity or high sensitivity. Next one, that is the resistance of the strain gauge must be as high as possible to minimize the effect of undesirable variation of resistance in the measurement circuit. So the resistance of the wire should be high to minimize the undesirable variation. So whenever we are measuring some stress with the help of our strain gauge or with the help of our resistance wire strain gauge, the resistance of that wire should be very much of high and it is not vary with respect to different environmental condition. They must have a low resistance temperature coefficient to minimize error on account of temperature variation that affect the accuracy of measurement. So the temperature coefficient should be very good of our resistance strain gauge, because if our in our environment our temperature is going to change rapidly, at that time it is going to affect the accuracy of our strain gauge, right? So that's why we must have low resistance temperature coefficient. Then after, the strain gauge must not have any hysteresis effect in response. So we already studied about the hysteresis in first chapter, right? So strain gauge must not have any hysteresis, because if it have some amount of memory for the previous value, then it have some amount of hysteresis effect, and which is going to affect our present value. So we need to minimize that effect. To maintain the consistency of calibration over a complete range, it must have a linear characteristics. So our characteristics should be linear. We also know about the linearity of the instrument, that is the variation in resistance must be a linear function of the strain. They are used for dynamic measurement. Okay, dynamic measurement, it means our value, or we can say our input value, is changing rapidly with respect to time. Hence their frequency response must be good. So rapid change in input should be measured by our instrument. So the frequency response must be very good. The linearity must be maintained within the accuracy limit over a complete frequency of the range. So linearity that must be maintained over a entire range. Okay, so next one, that is the resistance wire material. Now no single material is able to satisfy all the different property. Okay, so we require the composition of different two material or three material to make our cable. Okay, a number of metal or alloy are used to make the resistance wire right now, and some of them are explained or we can say derived in this table. So over here material, so nichrome, so Ni 80 percentage and Cr that is 20 percentage, and over here we can see the gauge factor. Over here Ni is the nickel and Cr is from indicating chromium, and atomic weight of the or atomic number of nichrome is 28 and atomic number of the chromium is 24. So we are mixturing 80 percentage of nichrome and 20 percentage of chromium, so the gauge factor is going to be 2.5. Its resistivity ohm per meter is 100 into 10 raised to minus 8, and temperature coefficient over here and upper limit temperature coefficient here. Then after constant, then after isoelastic nickel and platinum. So these are different material, for that different gauge factor are going to be indicated, and resistivity is going to be also changed with respect to the material. Okay, so please note this down in your note. Then after we are going to see the backing material. Okay, now the backing material is that part of the strain gauge to which the strain sensitive grid structure is attached. Okay, we are attaching our strain sensitivity structure. Now in addition to the primary electrical installation, backing it helps to retain the geographic shape of the grid pattern to provide protection to the grid. So backing material is going to provide the protection to our resistance wire strain gauge, right? So no damage is going to be there to our cable. So backing material is going to be protect our gauge or protect our resistance wire. The type of backing material used, their temperature range and characteristics are given in table. So there are different types of backing material which we can use in our strain gauge. So starting with the paper, epoxy paper, then after phenolic paper or bakelite, fiberglass, then after transfer glass, glass waves, and so on. Okay, so these are the adhesiveness of different gauge backing material. Then after curing time, its pressure type and which temperature range it can handle. So this is also important whenever we are selecting our backing material for the strain gauge. Now next one, that is the adhesiveness. Okay, adhesives, that is what they are the bonding material that are used to fix the strain gauge on the test specimen. Okay, which are used to bonding the strain gauge to the test specimen. Successful bonding depend on correct surface preparation and use of correct bonding agent. So we are connecting our, or we can say we are bonding our resistance wire with the backing material with the help of adhesives. Okay, the bond has to be formed between surface that is to be strained and the plastic backing on which the gauge is mounted. Over here we clearly mentioned that the bond has to be formed between the surface that is to be strained, that is our resistance wire, and the plastic backing on which the gauge is mounted. Improper bonding can be cause many errors like hysteresis, creep, temperature introduce, zero drift. Then after drifting error can be also introduced in our instrumentation, low insulation resistance, etc. Different type of error are going to be there if bonding is not proper between the backing material and the strain material. Okay, it is recommended that the adhesive material must be of quick drying type. Okay, it must be insensitive to moisture and good adherence. Then after different type of material like cement, chemical reacting cement, and bucco cement, different cement are going to be used as a adhesive material to bond two material, that is the strain gauge and backing material. So at the main reason, or you can say main use of adhesiveness is to bonding to different type of materials. Now Next, that is the last one, that is lathes. Okay, the lathes should be of such material that have low and stable resistivity, because lathe is the point from where we are going to take our output of the resistance, right? And low resistance temperature coefficient, because we are putting it into a different environment, so the change in temperature should not affect our lathes very much of frequently, right? Now next one, that is the gauge technique and others factor. Okay, the proper operation of the strain gauge depends on the quality to be of bonding that hold the gauge of the surface of structure that undergoes to the test. Okay, whatever the structure undergoes, it is going to depend on the quality of the bonding. Next, that is if the bond does not transmit the strain from the test piece to the wire or foil of u gauge, the result obtained on the measure can never be accurate, because if the bond is not proper and all the force is acting on the strain gauge is not taken by the resistance wire strain gauge or strain gauge, and only it is going to taken by the backing material, then there are some error, or we can say we are never going to get accurate result. So the force is need to be transmit to the strain test piece. Okay, the factors on which the operation of strain gauge depends are here. So we are starting with the installation. So first of all, installation, the size of a strain gauge is an important parameter for measurement faithfulness. The drawbacks of gauge size are, first one, that is the gauge size in physical. Okay, the gauge size must be such that it must fit into the available surface of the specimen. So size should be adjustable or minimum size, so it can adjust anywhere in our surface. Then after, the strain gradient at the location where strain is mounted will average output strain below its strain sensitive grade. Now, the wavelength of the vibratory strain must be large as compared to the wavelength or length of the gauge to reduce the error in the dynamic response, because we are changing our input with respect to the time. So, for the good fidelity in the magnitude of strain production, the gauge length must be less than 1/20th of the wavelength of the vibration. So, we are neglecting the error with the help of this type of arrangement. And the large possible size of gauge must be used, as the gauge will have lower hysteresis, creep, or zero drift and large current carrying capacities. So the strain gauge circuit must have high input impedance, because the resistance need to be very high. Okay, and the surface on which the strain gauge is mounted must be very smooth, so there are no error, or we can say all the stress that are applied on the stress test paper or stress state material, it is going to be measured very much of accurately, and all the scales, rust, paint and other surface contamination must be removed from the metal surface. So we frequently need to clean our strain gauge, right? Now talking about the next topic, that is hysteresis. Okay, the bonded strain gauge must sense the same amount of strain as that is experienced by the surface to which it is bonded. So bonded material is also going to experience some amount of force or some amount of stress, which is exactly same amount that is sensed by the strain gauge. And figure, here we have one figure which shows the loop of the cycling loading. So starting with, this is the one, after that it is going to be in negative direction. So over here this is not going to be 0, but at some value point, from that it is going to 3, then after 4, 5, 6 and so on, it is going to be increasing. And this is inside of the micro strain. Okay, this is inside of the micro strain, and over here that is the change in resistance divided by the actual resistance, and this micro strain, that is change in length divided by the actual length, or you can say strain. Okay, if the repeated cycling is done to the strain level higher than the required, then the hysteresis effect will be reduced. A large hysteresis can arise from faulty bonding technique. It cannot be eliminated by cycling. Okay, if there are fault in our bonding, then we cannot eliminate it by cycling, or we can say by number of turns of the input. Now next, that is fatigue life. Okay, Fatigue like failure arise because of stress reversal that occurs at a point where the connecting leads are attached to the strain gauge. So after some time, or we can say after tiring effect aging of the instrument, the leads are going to connect to from the output side. Okay, we are connecting our measuring device with the leads. So at that point, if there are some amount of stress applied, then we cannot get our accurate result. It can cause decay in the base of gauge or fixing cement, resulting in filament relaxation. For dynamic test, etched foil gauge are preferred over wide gauges. Isoelastic gauge are most convenient in these situations, and the gauge lead must be well secured to prevent relative motion between gauge and leads. They should not have abrupt change in area at that joint. So we already know about the leads, because leads are also important in our strain gauge factor. Next is hysteresis and moisture effect. So the moisture absorbed by the bonding cement or gauge backing cement cause volume change that can elongate or compress our grid. So this is very important term. Whenever the moisture is over there, our bonding cement, or what is our baking cement, or whatever our baking material, that is going to absorb that moisture or humidity, and it is going to change its original shape. It is going to be either increase or decrease in size. So that is going to apply some amount of force to our gauge or gauge grid, and this is what going to introduce some amount of error, which we cannot neglect. The humidity effect can be eliminated by bonding the gauge in dry condition, right? And heat is applied through the operation. So humidity can be eliminated by bonding gauge to the drying process and heating process. The defect is observed by the sharp fall in insulation resistance between the gauge and the specimen. Optimum gauge protection method must be adopted. So we require calibration of our gauge by some duration of time, and we cannot neglect the effect of humidity and moisture in our strain gauge measurement. Next, that is creep. For good bonding with the truthful transmission of the strain to the gauge, it is required that the backing material in which the gauge filament is embedded and the bonding cement holding the gauge in position is stronger than the filament. So always we require this type of arrangement. In this condition is not met, then the gauge filament relax under the strain, and the strain indicate it as less than the true strain value. Okay, so we required it to be very much of good bonded, and it is not that much loose or not that much tight. If it is that much amount of loose, then we cannot get the actual amount of strain, and if it is very much of tight, then we are getting higher value than the applied strain, right? So it become a non-linear with increase in the strain. And creep occurs due to the number of sources, that is mainly because of the faulty structure in the gauge itself, faulty bonding, or increase in the temperature. So whenever temperature is going to increase, the gauging effect are there. So the length of the cable is going to be increased, or the material size of the baking material is also going to be changed. So it is going to introduce some amount of creep. The creep is time dependent. It is more than the gauge are initially installed. Okay, creep effect is more significant in smaller gauge because the smaller bonding area. So smaller our size of the gauge, the creep effect should be there in our gauge. Next is the temperature effect. This is the last effect. The change in temperature affect strain measurement. Okay, change in temperature affects strain measurement. How? There is a change in gauge resistance and differential expansion of gauge element result in tension or compression. Okay, tension or compression depending upon the value of temperature, that is either increasing or decreasing. It can be avoided by correct selection of the gauge material. So while selecting the gauge material, we need to mention, or we need to take in account, take in mind that temperature effect are there in our strain gauge. So if temperature is going to be increased, then the length of the gauge is also going to be increased, and there are also creep that is going to be introduced in our strain gauge. And if the temperature is going to be decreased, the length of the gauge is going to be reduced, right? So same effect are going to be observed. So lots of amount of error are going to be introduced in our measurement. If short leads of wire having opposite temperature coefficient are connected in series with the gauge, then the temperature effect can be reduced, because if our material or our strain gauge material is the positive temperature coefficient, we can directly connect it with negative temperature coefficient and we can eliminate both the effect, right? Practically, the error are eliminated by connecting the gauge in differential pair in Wheatstone bridge circuit by placing temperature composition element circuit. Okay, what is Wheatstone bridge circuit? We are going to study it in the next chapter, or we can say next lecture. But right now, to eliminate error, we can connect the differential gauge in Wheatstone bridge arrangement. So with the help of Wheatstone bridge, we can eliminate the temperature coefficient effect, and which is we are going to study in the next video lecture. So these are some important GTU questions that are asked in your examination and very important with respect to your examination. So please note this down, which we are already covered in this video session. And if you have any kind of query regarding
The next experiment is how to characterize a strain gauge sensor. The aim, theory, procedure, review questions, references are already there with the experiment. You are advised to read carefully the theory first, then procedure, and then perform the experiment. Go to simulator. Now you can click here for simulator. Now this experiment, you will have a lot of configurable parameters. This experiment is of two levels. In level 1, you are selecting what will be the material of construction of strain gauge. For example, I have selected copper as a material. Input voltage for excitation 5 volt DC. The resistance which I have selected for strain gauge is suppose 120 ohm, and the configuration, there are 4 types of configurations you can have. One is called as quarter bridge, half bridge in adjacent arms, half bridge in opposite arms, and full bridge. Now in this case, if I select full bridge, you will find that these strain gauges, all the strain gauges and all the arms of this bridge are active. Instead of that, if I select half bridge opposite, you will find strain gauges are kept in opposite arm and the fixed resistors are kept in the opposite arms. Instead of that, if you go for half bridge in adjacent arms, you will find the configuration would be like this. And then if you go for quarter bridge, only one strain gauge would be available and would be connected in the bridge. Now, each configuration has got distinct advantages and limitations. You are advised to read the theory carefully, and as per your application, select whether the configuration should be quarter bridge or full bridge. Then select the gauge factor. Gauge factor is varying from 0.9 to 8.5. Suppose I have selected 0.9 as gauge factor, and then configure the entire system. Once you have configured it, you will say yes. Indicates that the material of construction is copper, input voltage is 5 volt, resistance is 120, gauge factor is 0.9, and quarter bridge you have selected. Now you will have to keep on adding weights on this cantilever beam, and the strain gauge is installed at this point where the maximum sensitivity would be there. So you will select how much weight you want to add. For example, if you have added 0.5 kg, the RG value or the gauge value, resistance of the gauge would be 120.0136. Then calculate output voltage in millivolt by using this formula. So this formula is dr equal to gauge factor into dl by L into R, where you have already given all the details about the applied weight, distance from load point to HG center, width of cantilever, thickness of cantilever. All this are given. Please read it carefully. Use this table for Young's modulus linear expansion coefficient of strain gauge. After solving this, enter value of output in millivolt. You will have to do this exercise 3 times. Now change the position, or I'm sorry, change the weight. Suppose I have added 4 kgs and I'll calculate what will be the output of strain gauge in millivolt if you have added here a weight of 4 kg. Submit it. It's correct. Then change this to suppose 8 kgs and then submit. After 3 readings, the plot will be available. Now this is the characterization curve of weight versus output in millivolt if you have connected strain gauge in a specific configuration as mentioned before. Now you will find that level 2 is now on. Now level 2, if you click on to level 2, this is used to demonstrate the effect of position of weight on the output of the strain gauge bridge. Now select here the position in centimeter. For example, if I select position in 16 centimeter or if I select 10 centimeter, this is 16 centimeter and this is 10 centimeter. The last weight we added was 8 kg, so this weight would remain as 8 kg. The output will become 1.41. You go on changing these values, you will find the output weight will go on changing. So if you add here 9, output voltage in millivolt will become 1.27. You can plot a graph. Now the graph will indicate that according to position how the output of the strain gauge is changing without changing the weight. And because of this, now you are eligible to go for level 3. Here load is connected maximum away from strain gauge, that is 16 centimeter, and the output is 2.26 millivolt. In all other cases you will find that the output was reducing, naturally the bending moment is less. Now go to level 3. Now level 3 is identifying what will be the effect of temperature on the performance of strain gauge. The RG value or the resistance of the gauge, which we have considered as 120.2169, is at 20 degrees Celsius. Now if I expose this to 30 degrees Celsius, what will happen? The new value of RG will become 115.28. Now if you will go on changing this temperature, the new value will go on decreasing. So in other words, if the temperature is 10 degrees, 120 becomes 24.97. So in other words, as you are increasing the temperature, resistance will go on decreasing. So here for 40 you get some value, but if you expose it to 10 degrees you get higher value. Now this is how 3 stages of experiment can be proved. One is the bridge configuration, it's called as level 1. Level 2 is position of the weight, and level 3 means what will be the effect of temperature on the performance of the strain gauge. Now this calculation will clearly reveal that there would be effect of change in temperature on the performance of the strain gauge. Hence, if you are measuring strain,
Hello friends, welcome to engineering tutorial. Today we are going to study about another transducer which is a strain gauge. It is basically a resistive transducer. So it's based on resistance or change in resistance or property of resistance. So let's get started. So what is a strain gauge. Now a strain gauge is basically a primary transducer. It's a primary transducer. So it's a primary transducer. It means that it converts physical quantity which is under measurement into mechanical signal. A mechanical motion or displacement, any type of mechanical signal. So it is a primary transducer which is basically used for measurement of strain, stress, displacement, force and pressure. These physical quantities are measured with the help of a strain gauge, and as it is a primary transducer, in order to convert the output into suitable voltage or current signal, we have to use a secondary transducer or a signal conditioning circuit. So what's the operating principle of a strain gauge? Strain gauge operates on the principle of piezoresistive effect. As I said, it's based on change in resistance. Its property is based on resistance, which is called as the piezoresistive effect. Now, what is the piezoresistive effect? Now, we know that the resistance of any material is given by the formula R is equal to rho into L by A. We know R is the resistance, rho is the resistivity of the material, L is the length of the material, and A is the cross-sectional area of the material. Now, here there are three important things to take note of. Resistance is directly proportional to resistivity, resistance is directly proportional to length, and resistance is inversely proportional to cross-sectional area. So it means that if resistivity increases, resistance will increase, and if resistivity decreases, resistance will decrease. Similarly, if length increases, resistance will increase, and if it decreases, it will decrease. But resistance is inversely proportional to area. So if there is an increase in area, there will be a decrease in resistance, and if there will be a decrease in area, there will be an increase in resistance. These are the three things which are exploited in the piezoresistive effect to construct a strain gauge and to measure physical quantities such as force, pressure, strain, stress, etc. So as I said, there are three possible ways in which there can be a change in the resistance of the material. There will be a change in length, or a change in cross-sectional area, or change in resistivity. In this, in the case of strain gauge, change in resistivity does not play any part. Only the change in length and change in cross-sectional area is considered. Change in resistivity takes no part in the strain gauge. So, first let us consider change in length. As I said, the resistance of a material is directly proportional to the length of the material. So, as the length increases, R increases, it increases, and vice versa. Means if length increases, R increases, and if L decreases, R decreases. So here we have tried to put it in terms of a mathematical formula. So let us say that the initial resistance is R, and the length of the material which is subjected to compression or expansion is changed by a factor del L. So if there will be an increase in the length, which is given by the positive sign, there will be an increase in resistance by a factor del R. If there will be a decrease in the length, minus del L, there will be a decrease in the resistance by a factor minus del R. A is constant. Here there is only change in length which is considered. Similarly, let us then consider change in cross-sectional area. Resistance of a material is inversely proportional to cross-sectional area. So, if cross-sectional area increases, R decreases, and if area decreases, R increases. Here, the resistance, let us say the initial resistance of the material is R, which is going to be subjected to any force or pressure leading to compression or expansion, and due to that there will be a change in the cross-sectional area. So, an increase in the cross-sectional area denoted by the positive sign here will lead to a decrease in the resistance denoted by the minus sign by a factor del R. And if there will be a decrease in the cross-sectional area due to stretching or expansion of the material by a factor del A, there will be a corresponding increase in resistance by del R, which is denoted by positive sign. Now, there are two important things here. As length is directly proportional to R, the notation plus minus sign, they are the same in both the cases. But here in cross sectional area it is opposite. Here it is minus plus, here it is plus minus, because here resistance is inversely proportional to cross sectional area. So, always make note of this. Do not ever write plus minus in this case of cross sectional area, it will be wrong. So, resistance is directly proportional to length and inversely proportional to cross sectional area. Let us try to understand it. Suppose, let us say there is a material, this large cylinder. It is a material, it has initial length L and diameter D. Suppose it is subjected to an expansion force, it is stretched because of this applied force, it is stretched. So, it undergoes expansion. Because of expansion, there is an increase in the length of the material and the length increases by a factor del L. But because of expansion, the diameter of the cylinder or the material, it decreases by a factor del D. As a result of that, the cross sectional area also gets reduced. Now, because of this applied force and expansion, there is an increase in the length. So, there will be an increase in resistance, because resistance is directly proportional to length of the material. But as the cross sectional area gets reduced, there will be a increase in the resistance as well, because cross sectional area is inversely proportional to resistance. So, in both the cases there will be increase in resistance, as both the factors, that is increase in length and decrease in cross sectional area, support an increase in resistance. Okay. So, in both the cases there will be an increase in resistance. So, normally the strain gauge comes in this configuration. It consists of a number of turns of wires which are wound over two platforms. Out of these two platforms, one of the platform is fixed and the other one is movable. Now, the force or the pressure or the displacement or motion which has to be measured is generally applied on the movable platform, so that whenever there is a force which is applied, there will be compression or expansion in these wires. Now, because of compression or expansion, there will be a change in the resistance in these wires, and this change in resistance is converted into suitable voltage or current signal with the help of a signal conditioning circuit, which is basically a Wheatstone bridge. So, here we use a Wheatstone bridge for signal conditioning, and the strain gauge is used in one of the arms of the Wheatstone bridge, and the voltage output is taken across these two ends, the opposite ends across which the DC supply voltage is given. So, the opposite ends, across the opposite ends, the output voltage is taken, it is amplified and is given to a digital readout or a pointer scale indicator. So, basically Wheatstone bridge is used for signal conditioning. So, the resistance of the strain gauge, it forms one of the arms of the Wheatstone bridge. Now, uh, there are two important parameters which are associated with the piezoresistive effect or the strain gauge. Those two parameters are the Poisson's ratio and the gauge factor. These two parameters are very important when it comes to strain gauge or the efficiency of a strain gauge. Now, what is Poisson's ratio? The Poisson's ratio is generally defined as the ratio between the per unit change in diameter of the material divided by the per unit change in length. It is also written as the ratio between the lateral strain and the longitudinal strain, which is given by del D by D by del L by L. This is called as, this expression is for Poisson's ratio and is generally negative, the negative sign. Another factor which is another parameter which is associated with strain gauge is the gauge factor. Now, what is gauge factor? It is defined as the ratio between the per unit change in resistance of the material divided by the per unit change in length, which is expressed mathematically as del R by R by del L by L. This is gauge factor. Now, both Poisson's ratio and gauge factor are related with each other. So, the relationship between Poisson's ratio and gauge factor can be written as 1 plus, so the gauge factor is equal to 1 plus twice of the Poisson's ratio plus ratio between per unit change in resistivity by per unit change in length. So, as I said, the change in resistivity is generally ignored in case of strain gauge. It is not considered. The change in resistivity is not considered. So, you can just write down that gauge factor is equal to 1 plus 2 into Poisson's ratio, 1 plus twice of the Poisson's ratio. This is gauge factor. This is the relationship between Poisson's ratio and gauge factor. Now, some of the materials which are used for construction or the building strain gauges are listed below. They have the resistivity and gauge factor values are also given. You can note them down if you want. So, basically platinum is used, platinum and nickel is basically used for construction of strain gauges along with constantine nichrome, and other semiconductor strain gauges are also available. Then there are bonded and unbonded strain gauges which are also there. There are many materials used, but these are basic four materials which are generally used for strain gauges. So, the resistivity and gauge factor values are given. You can note them down if you want. So, here we have studied the basic principle of operation of strain gauges. So, as I said, there will be either a compression or expansion of the material. Now, if there would have been compression here, there would be compression of the material, there would have been an increase in the diameter leading to an increase in the cross sectional area and a decrease in the length. In that case, there would have been a decrease in the resistance, as both decrease in length and increase in cross sectional area support a decrease in resistance. So, these are the normal things which happen in a strain gauge. There will be either compression or expansion. In case of expansion, there will be an increase in resistance. In case of compression, there will be a decrease in resistance. Why? Because
Hi, welcome to Training Tutor. In this video, we are going to see the characteristics of strain gauge measurement. Following equipment required for conducting strain gauge measurement. First one is the strain gauge measurement trainer kit. Second one is the load cell. Third one is a multimeter. And fourth one is some weight. This is a basic circuit diagram of strain gauge measurement. Here, the 5 volt DC supply is given to the sensor. Here, load cell used as a sensor. The load cell consists of 4 strain gauge. That 4 strain gauge formed like a bridge circuit. The output of the bridge circuit is connected to the instrumentation amplifier. The function of the instrumentation amplifier is to amplify the lower signal that produced from the bridge circuit and also reduce the noise in the bridge circuit. Okay. After amplification, the signal is given to the inverting amplifier and non-inverting amplifier. That inverting and non-inverting amplifier provide the calibration. This is a load cell. It's made by 4 strain gauge. Top side having a 2 strain gauge and the bottom side have 2 strain gauge. The top side is fixed point. Top side is fixed one and bottom side is movable one. The movable side we connect the load balanced. Okay. Before going to start the experiment, first we need to calibrate the strain gauge. The actual value is now 0, but it shows 250. So by varying offset, we make it 0. The offset point is very sensitive, so I have to vary very slowly. Yeah, now the kit at most 0. Then connect voltmeter. See, the voltmeter readings also 0, similar to in the kit. The kit shows the value in the gram. Now I am going to add 100 gram. Now see the value in kit, it shows 100 gram. At the same time, in the voltmeter, the electrical output is 0.5 volt. Okay. Again, I am going to add another 100 gram. Now the value is 200 and the electrical output is 1 volt. Okay. Then I am further adding one more 100 gram. Still now I added 300 grams. So now the kit shows 300 or 300 305. So it's due to some calibration problem, and the voltmeter also shows 1.5 volt. This is a tabulation of strain gauge measurement. For first 100 grams, the voltage is 0.5 volt and measured weight also 100 gram. For second 200 grams, the 1 volt voltage electrical output and measured weight also 200 grams. For third 300 grams, the 1.5 volt and then measured also 300 grams. This is a graph of strain gauge measurement. In the x-axis the weight in grams and y-axis voltage electrical output. Okay, for we have taken 100 grams, it shows 0.5, the 200 grams shows 1 and 300 grams it shows 1.5. So finally it produces the linear output. Okay, this is the way of obtaining characteristics of strain gauge measurement using load cell. I hope this video gives some clarity about strain gauge measurement. Thank you.
Hello guys, this is Siddharth Saratkar and welcome back to your own channel Explore Electronics. And today we are going to talk about another interesting stuff, and this time it is strain gauge. So let's begin without wasting much of your time and my time. So let's begin. Before getting into it, we should know that what is the work of a strain gauge. So as the name suggests, it is used for the calculation of strain and associated stress in experimental stress analysis. Now if I have to tell you the basic working of this device, then it is a metal conductor. If stretched or compressed, its resistance changes on account of the fact that both length and diameter of the conductor changes. Also, there is a change in value of the resistivity as rho is equals to Ra by L, where A is the cross-sectional area and L is the length of the wire or the conducting material whatsoever you are taking it, and R is the resistance offered by the particular thing, the conductor. These types of strain gauges are known as piezo-resistive gauges. Now let's work out the types of strain gauge. Strain gauges can be mainly classified into 7 types. Number 1 is unbonded metal strain gauge. Number 2, bonded metal wire. Number 3, bonded metal foil. Number 4, vacuum deposited thin metal film. Number 5 is sputter deposited thin metal film. Number 6 is bonded semiconductor, and number 7 is diffused metal. So in this video we would be talking about unbonded metal strain gauge and bonded wire strain gauge. If you want me to make more videos on the remaining types, so let me know in the comment section. So let's start with unbonded metal strain gauge. But before that, it is advisable to know about gauge factor. So gauge factor is known as the ratio of per unit change in resistance, which is delta R by R, is to per unit change in length, that is delta L by L, which comes out to be G is equals to delta R by R divided by delta L by L. Now this is how an unbonded metal strain gauge looks like. It has various components such as diaphragm, forced rod, strain gauge windings, spring elements, etc., and within it an arrangement of Wheatstone bridge is set up. Now pay a little bit concentration on the working part. So whenever the whole setup experiences a strain, a displacement of 0.004 mm is observed on the two sides of Wheatstone bridge due to the tension created in the strain. As the Wheatstone bridge gets disbalanced and produces an output voltage which is proportional to the input displacement and hence to the applied pressure. Now coming to the sum of the statistics, electrical resistance of each arm is 120 ohm to 1000 ohm, and the input voltage should be around 5 to 10 volts. At number 2 is bonded wire strain gauge. This type of gauge consists of a grid of fine resistance wire of about 0.025 mm in diameter. The grid is cemented to carrier, which is a thin sheet of bakelite or a sheet of Teflon. A sheet is covered on the top to prevent the material, as the material used for both bonded and unbonded strain gauge are same. So you can say that the gauge factor is comparable. Size of the strain gauge varies with the application from 3 mm to 3 cm. Now there are some factors under which the apparatus will provide an excellent result. Number 1 is strain gauge should have a high value of gauge factor, as it indicates large change in resistance, which accounts in high sensitivity. Number 2 is strain gauge should have a low resistance temperature. This is done to account the error minimization of temperature. Number 3 is the strain gauge should not have any hysteresis effect in its response. Number 4 is linearity of the function should not be changed. And there are many more points, but the above mentioned points are more important. So here we come to the end of this video. Thank you for completing my first milestone of 100 subscribers, and for more information do subscribe my channel. If you have any suggestions, ideas, then
Hey Daryl, what are we looking at here?
Hey Danielle, this is a new display that we've recently put up in the training center that shows the wide variety of different types of strain gauges that we offer. As you sort of scan around this demonstration or example, you'll see a collection of very small uniaxial strain gauges. We build uniaxials anywhere from 0.008 of an inch active length, little small ones like this one, all the way up to strain gauges that are 4 inches long like this one here. This is one that's commonly used for concrete testing. And we've got a combination not only of the uniaxial gauges, we also have some examples of shear pattern gauges like this one. For example, like if you're trying to measure torque on a tube or a shaft, That's a really good one to choose. This is another example of a shear pattern gauge. In addition to that, we also have some T rosettes and rectangular style rosettes and even delta rosettes that are in here. This is an example of a larger size 3-element stacked rosette. This is an example of a 3-element delta style rosette, and the difference between this one and this one is that this one is stacked and these grids are at a 45-degree angle from each other, and this one is a planar style rosette and these grids are at a 60-degree angle from each other. In addition to that, you'll see some other kind of unusual or unique gauges like this big one that's right here. This is a circular diaphragm gauge. So if you were to take a pressure transducer and take it apart and look inside, you might see a gauge inside it that looks just like that.
Well, Daryl, I've also noticed that some of these gauges have wires attached, like so. What are this?
Exactly. Some customers would like to get the gauges with pre-attached wires that'll make the installation of the gauge a little bit easier for them. So oftentimes we'll take the basic gauge and then we'll add on some whisker leads so that really all the soldering they have to do is back over at a terminal as opposed to maybe some very small tabs on the gauge. If you look down here at this very small circular diaphragm gauge, you'll see what I mean. This one is little small pattern, very small fine connections, and putting those leads on it really makes that a whole lot easier.
Now I understand. Great.
So as you see, there's a wide variety, thousands of different strain gauges that we manufacture, hundreds of different gauge patterns, and this is just a small sampling of those to kind of give you an idea of the range of products that we can manufacture.
Cool. Thanks.
You're welcome.